Welcome, everybody, to PALS this week. Today's speaker is Anna Romanowska, and she will speak to us on algebraic properties of dyadic convex polygons. Anna?
Thank you. So at first, I would like to thank Peter for inviting me to give a talk, and I would like to thank the organizers of PALS for organizing this very interesting international meetings. So as Keith said, the talk will be about a certain algebraic approach to dyadic convex subsets of affine spaces over the ring of dyadic numbers. So let me comment on the title. First, let us recall that the dyadic numbers are just rational numbers whose denominator is a power of 2. They form a principal ideal subdomain of the ring of real numbers. And this is the smallest subring of R, containing all integers and invertible 2. So dyadic numbers are present in many areas of mathematics and applications. So let me mention 2 examples. Dyadic numbers have finite binary expressions, so they are present in digital computers. And in physics, they are used to model spaces with holes. Now, the geometrical objects we will be interested in are affine spaces, or if you prefer to call them affine modules, over the ring of dyadic numbers and their affine and their convex subsets. The precise definitions will be in a moment. We will describe these 2 structures in purely algebraic way as algebra sets with certain operations defined on them. Our interest in such algebras developed in the framework of our investigations on idempotent entropic algebras we called modes. At present, the theory of modes has two monographs written by Jonathan Smith and myself from 1985 and 2002. And there are, of course, so many papers developing many topics contained in the book. 2 of the main classes of modes are given by affine spaces or affine modules over a commutative unital rings and convex subsets of affine spaces over reals. We were interested in generalizing the concept of convex sets to convex subsets of affine spaces over more general rings. And it turns out that the ring of dyadic numbers is a very good candidate. The ring is ordered. It has non-empty open unit interval we use to describe convex sets. The structure of modules over the ring of dyadic number is very well known and clear. And additionally, when we started to work on such structures, there were already available some results concerning algebras we used to describe such convex sets coming from work of Jerzek and Kepka. The talk will be organized as follows. At first, I will tell you about our approach to real affine spaces and real convex sets. Then the second part will contain definitions and basic properties of affine spaces over dyadic numbers and dyadic convex sets. with special emphasis on dyadic intervals and dyadic triangles, which are essential to build more complicated polytopes. And the last third part will contain the recent results obtained together with Anna Mućka concerning the full description of dyadic triangles, their classification, characterization, and representation. So let us start with very elementary situation. So consider the Euclidean space R to the n, where R is the field of reals, and the traditional definition of an affine space over the field of reals and more general fields is usually done by means of an action of the group of the vectors of vector space R to the n over the space of points R to the n, satisfying the known conditions. But the affine spaces may be also defined in a different way. So let us note that for any points x, y in R to the n, the line through x and y consists of all binary affine combinations of points x and y, here denoted by xy underline p. And the subset A of R to the n is a non-trivial affine subspace of R to the n if, together with any two different points x and y, it contains the line through these points. In other ways, when A, the set A, is closed under all these binary affine combinations. Now the line segment joining the points x and y is given by the same binary affine combinations, but with p running over the elements of the open unit interval, I-O. So a subset C of R to the n is a non-trivial convex subset of R to the n if, together with any 2 points x and y, it contains the line segment joining x and y. In other ways, C is closed under these binary convex combinations. Let us note immediately that the algebra A is also closed under all affine combinations obtained by composing binary ones, and the second algebra C is closed under all convex combinations obtained by composing binary convex combinations. So these two types of algebras motivate our general definition. First, let us concentrate on affine spaces. So let R be now a subring of the ring of reals. We will say that an affine space A over R, or affine R space, is just the algebra A with all these affine combinations as basic operations. So the sum of coefficients equals 1. And if 2 is invertible in R, then this algebra is equivalent to the algebra A with binary affine combinations as defined on the previous slide. These algebras have two very interesting, important properties. And the first one is that these algebras really correspond and describe precisely affine spaces defined in a traditional way. And the proof may be found in our book on modes, for example. And the second very important property is that for a given ring R, the class of affine R spaces is a variety, the equationally defined class of algebras. So this theorem, this way of describing the class of affine R spaces goes back 1960, to the paper of Osterman-Schmidt. This was probably one of the first, considering these spaces in this way. But there were also other approaches, similar approaches and papers by other people. Let me mention here two series of papers from 70 and at beginning of 80 by Bela Chakan and by Agnes Sendrey. They usually call these algebras affine modules. We prefer to use the traditional name affine space, but this is, of course, the same. Now let us go to convex sets. This time we will assume that R is a subfield of the field of reals. And convex subsets of affine R spaces are just the subreducts of these spaces with respect to binary, to convex combinations. That means these affine combinations with coefficients from the open unit interval. In particular, real convex polytopes are finitely generated convex sets, and these polytopes are generated by the vertices. And real polygons are finitely generated convex subsets of the real plane. Now, the class of convex sets considered as such algebras is not a variety. Convex sets the class is not closed under homomorphic images, but it generates the variety of barycentric algebras. The variety and these algebras are now very well known. And there were, in 70s, there were a series of papers written more or less independently by several people, considering such algebras and the variety of barycentric algebras. But probably one of the most important is the paper of Walter Neumann from 70. So he characterized barycentric algebras, found the unique non-trivial subvariety, where these all operations are equal and in fact are equivalent to Selmy lattices, and classified convex sets of barycentric algebras as a quasi-variety of cancellative barycentric algebras. Now let us go to dyadic convex sets. So we will consider again the ring of dyadic numbers. And a dyadic convex sets can be defined just as the intersection of real convex set in R to the k with the space D to the k. And dyadic polytopes are the intersection of the space D to the k with a real polytope in R to the k, but with vertices in the space D to the k. One of the most important examples of such dyadic polytopes is given by simplices. So dyadic simplices may be defined similarly as real simplices, namely n-dimensional dyadic convex set with n+1 vertices generated by these vertices is a dyadic simplex. Now, dyadic triangles and dyadic polygons are respectively the intersection with the dyadic plane of a triangle or polygon in real plane, having vertices in the dyadic plane, of course. And the dyadic intervals for the one-dimensional analog. Note that dyadic intervals in this context are always considered as closed intervals. Let me mention that this is not the unique definition one could give of dyadic polytopes, and there are many subtleties concerning the definition, and there is I think, quite good discussion of the problem in a paper written by Gabor Cedli and myself, published in 2013. So we can do this definition more generally, but I think the definition I gave you just now is closest to the idea of convexity. Now, what are the differences between dyadic polytopes and real polytopes? So real polytopes are barycentric algebras A with these binary convex combinations. Similarly, we can define dyadic polytopes as algebras A with convex combinations, but with coefficients coming from the open unit interval of dyadic numbers. However, as shown already by Ježek and Kepka, each of these binary convex combinations is in fact generated by one operation, namely by arithmetical mean. So instead of considering infinitely many binary operation, it is sufficient to take this arithmetical mean as the basic operation. And the operation is idempotent, commutative, and entropic, or as some people call medial. So it is a mode algebra and additionally is commutative. So we usually call it commutative binary mode or CB mode. Let me recall that Ježek and Kepka used the name abelian for medial or entropic. They used this name entropic in a little different context. But this name abelian gave the abbreviation CIA, which has not the best connotations in Czechoslovakia of that time. So they changed the name to idempotent commutative medial groupoids. But we prefer to use this name CB modes. Now let us go further and see what are other differences between these real and dyadic polytopes. First, all real intervals considered as barycentric algebras are isomorphic. So, and they are isomorphic just to the unit interval, which is a one-dimensional simplex. And such a simplex is generated by its ends. Similarly, all real triangles are isomorphic, and they are isomorphic to two-dimensional simplex. Each of them is generated by its vertices. But this is not true for dyadic intervals and dyadic triangles. Consider the dyadic interval on the dyadic line with ends 0 and 3. So you may easily notice that 0 and 3 do not generate all dyadic numbers between 0 and 3. For example, you cannot get 1 or 2. So to generate the whole interval, one needs at least 3 generators. For example, you can take 1 or you can take 2. And since each simplex is generated by each interval, which is a simplex, is generated by the ends, so this interval 0, 3 cannot be isomorphic to the simplex. And to see how it is with triangles, take the triangles with 0, 3 on the x-axis, now in the plane, and at third vertex with at 1 on the y-axis. And you can easily see that these 3 vertices do not generate the polytope, because you cannot get all the points of the sides joining 0 and 3. So again, this triangle cannot be isomorphic to the two-dimensional simplex. class of convex subsets of affine R spaces was characterized by Walter Neumann as the sub-quasi-variety of cancellative barycentric algebras. In fact, this is the minimal quasi-variety of barycentric algebras, and all quasi-variety were characterized much later by young, at that time, Russian mathematician Ignatov. But if you consider now cancellative commutative binary modes, that it appears that this class contains infinitely many sub-quasi-varieties, and among them there are infinitely many varieties of commutative binary modes. The varieties were described by Kepka-Jerzek. So again, one more difference. So when we started to work on commutative binary modes, so the first problem was, basic problem, was which characteristic properties of real polytopes, in particular polygons, carry over to dyadic polytopes and polygons. And the special role is here placed by intervals and dyadic intervals and dyadic triangles. If you take any polygon, then one can divide such a polygon into the union of triangles such that the intersection of the interiors of any two of them is empty. For example, you can divide a polygon in such a way that you take any fixed vertex and join it with all other vertices that are not adjacent to this fixed vertex. And in this way, you have such division of a polygon into triangles. And now, if you take a polytope in 2 dimensions, then this polytope consists of the interior and boundary. And boundary consists of maximal walls, and each maximal wall is a polygon. So there is an inductive procedure in building more complicated polytopes. So the basic role is played by intervals and triangles. And so the next problem was classify all dyadic intervals and all dyadic triangles up to isomorphism. And isomorphism, when we work with isomorphism of dyadic polytopes, it is very helpful to have in mind that if you take 2 polytopes in the space, in the same affine space, the smallest affine space containing them, then isomorphism from one polytope to second polytope may be extended to the automorphism of the dyadic space. On the other hand, automorphism of this dyadic space can be restricted to isomorphism from a polytope to its image. And now, automorphism of affine spaces are just members of the affine group, and this affine group is generated by linear group and the group of transformations. So if we want to work with isomorphism of dyadic polytopes, we can always choose an arbitrary point as our origin and introduce the structure of a module, and then work with linear mappings and with transformations. So this is the very, very useful techniques we use very frequently. So with this problem of isomorphism, closely connected is the problem of generation. So first question, where are all dyadic intervals finitely generated? Are all dyadic triangles finitely generated? Dyadic intervals were already described in our first paper on dyadic polygons written by Katarzyna Matczak and Jonathan Smith, published in 2011. And the theorem says the following. Each interval of the dyadic line is isomorphic to some interval with ends 0 and k. We say that it is of type k, where k is an odd positive integer. And two such intervals are isomorphic precisely when the right-hand ends are equal. In particular, the interval 0, 1 is generated by its ends, and it is isomorphic to the one-dimensional simplex. But if k is bigger than 1, then we need at least 3 elements to generate them. In the same paper, we could show that each dyadic triangle is finitely generated. And as a corollary, we get that each dyadic polygon is finitely generated. And the proof is very combinatorial, considering many different cases. Then 10 years later, we came back to the generation process, and we could show, also together with Katarzyna Matczak and Anna Mućka, that each dyadic polytope is finitely generated. And the proof is based on the very clear basic idea. Each polytope consists of its interior and boundary. And boundary consists of maximal walls, and these maximal walls are also dyadic polytopes. So there is a certain inductive procedure in generating the boundary. But additionally, we should be certain that we can also generate the points in the interior. And to do this, we can use the fact that each polytope contains a simplex of the same dimension, which is the simplex sits in the interior of the polytope. So to generate the whole dyadic polytope, we have to generate the boundary and find the generators of this simplex inside. What was interesting was the fact that the polytopes are not the unique subgroupoids of d to the n, which are finitely generated. And we were able to show that a subgroupoid d of n-dimensional dyadic space is finitely generated precisely when its dyadic convex hull is a polytope with the same vertices and the same interior as d. And we can use, as an example of such a polytope, such a convex set, we can use the same examples we used when we spoke about generating triangles. Take this triangle in the plane with 0 and 3 on the x-axis and 0, 1 as the third vertex. And you can easily see that this convex set is not a polytope, but the polytope with these three vertices, contains this first convex sets. So this convex set with the side 0, 3 on the x-axis and 1 on the y-axis is finitely generated. So it's not so obvious to find the all generators, but we can do it. We have a quite nice example. Now, if we consider any dyadic triangle, then its sides are just dyadic intervals. So we can assign to each side its type. Type is always an odd natural, non-positive natural, natural number. And such a triple of types of sides is called boundary type. So you can notice that binary type depends on the orientation of vertices, and it is defined up to cyclic order. Now, a dyadic triangle is of right type if its shorter sides are parallel to the coordinate axis. And each triangle of right subtype is determined uniquely up to isomorphism by its boundary type. It is quite interesting if the types of shorter sides are, say, M and J, then the type of hypotenuse is just the greatest common divisor of J and M. So we called it, this is something like Pythagoras theorem. But the boundary type does not determine a general dyadic triangle. For example, we can take a triangle with vertices 0, 0, 2, 0, and 1, k. And if k is 1, then this triangle is just, this is a polytope, and it's two-dimensional simplex. But if you take, instead of 1, 1, if you take 1, 3, then this triangle we obtain is no more polytope. It is not generated by these 3 points. So it is not isomorphic to the first one. But both have types 1, 1, 1. And if you take as the third point 1k and 1l, where k and l are odd numbers, so the triangles we obtain are never isomorphic. So we have infinitely many triangles of type 1, 1, 1, which are not pairwise isomorphic. And there are triangles in the dyadic plane which are not isomorphic to right triangles. So, but this follows from our representation theorem. So it's a little more complicated to show examples. So recall that automorphism of dyadic plane transform a triangle in the plane onto an isomorphic triangle. And the first basic fact is given in the following lemma. Each dyadic triangle is isomorphic to a triangle ABC contained in the first quadrant with one vertex, say A, located at the origin, and the vertices B and C having non-negative integer coordinates. So this is very, very, very useful lemma. So I will skip this slide and will show you the illustration on the picture. Here is a general situation of such a triangle. And you may notice that if I and n both are 0, then we get a right triangle. If one of I and n is 0, then we get a triangle with one vertex on one of the axes. We call such triangles hats. And when a vertex A of dyadic triangle located at the origin is chosen, then the triangle ABC comes in one of 3 types. This was still shown in our paper with Matczak and Mućka. The 3 types are the following. These are right triangles, hat triangles, and other triangles. However, you may easily notice that this description depends on the choice of the vertex located at the origin. Then, when we were during our first work on this, say, classification, we were not quite aware or didn't pay attention that these three classes are not disjoint. In fact, we could prove quite a lot of different results, especially concerning generation using this description. But one mistake in technical lemma resulted in a wrong formulation of one conclusion, that such a quadruple I, J, and N determine a unique pointed triangle in the first quadrant. So we came back to these problems later on, and we were able to show improvement of this description and full classification of dyadic triangles. Two properties were essential in these improvements. First one, given in this proposition here, if I is an isomorphism between two dyadic triangles T1 and T2, and Pi is the area of the convex R hull. That means the smallest convex sets, real convex sets containing T1 Ti. Then the quotient P1 over divided by P2 equals 2 to the k. So this is one very useful property. And the second very useful property says that if P is a point of the dyadic plane with integral coordinates and not on any axis, then there is a d-module automorphism taking P onto a point of one of the axes, again with integral coordinates. So we can see from this lemma that the third class of the theorem, the other triangles, is in fact not necessary. So the new improved classification is the following. So assume that T is a dyadic triangle in the dyadic plane, then T is isomorphic to each of the following triangles with vertices with integral coordinates. The first one is a triangle ABC contained in the upper half plane of the dyadic plane, with one vertex, say A, located at the origin, another, say C, located on the positive part of x-axis, or this is a triangle ABC contained in the first quadrant, as in the previous theorem, with AC as above, but with third vertex B such that the first coordinates is between the points A and C. So we usually denote such triangles T, I, J, and 0. Here is illustration. If on the left-hand side figure, we have three possible situations of the triangle ABC. B2 give us the real hat as described in the second point, and the three hats show the more general situation of the point A. We usually call these hats either real hat or cracked hats. And on the right-hand side, there are isomorphic images of these three hats with prime denotes always the image of the corresponding vertex, and you can observe that this isomorphic this triangle obtained as isomorphic images has reversed orientation. Now, next proposition says that each triangle TIJM0 can be chosen so that these parameters are all odd. And the triangle TIJM, we usually drop 0 in this situation, is called representative hat. And theorem says that each dyadic triangle in the dyadic space D squared is isomorphic to a representative hat. So we can reduce the problem of isomorphism to isomorphism of representative hats, what is very, very helpful. We may also notice that each dyadic triangle is isomorphic to 3 representative hats with the same vertex orderings, and 3 isomorphic hats with the reverse orderings. They correspond to the 6 permutations of vertices. Now, isomorphisms of representative hats are considered as pointed-oriented isomorphism. That means preserving the pointed vertex and the vertex orientation. And we have the following proposition. Consider 2 representative hats, T with vertices A, B, C, and T prime with vertices A prime, B prime, C prime. And let I be a mapping taking B to B prime and C to C prime. Then I is a pointed-oriented isomorphism precisely when A is equal to A prime, B, C is equal to C prime, and B has as the second coordinate J, but the first coordinate I prime is such that J divide I prime minus I. So you may notice that the point B prime is on the line y equals to J. And the triangle T prime is a right triangle precisely when J divides I. As a corollary, we get characterization of pointed dyadic triangles. So for any positive odd integers J and M, there are J isomorphism classes of representative hats T, I, J, M. And each class is represented by a unique triangle T, I, J, M, where I is also odd, but from the set, but between 1 and 2J. And on the other hand, each pointed dyadic triangle is isomorphic to a unique triangle TIJM, where Jm are positive odd integers, and I is odd integer between 1 and 2J. So you can see that such triples IJM correspond uniquely to isomorphism classes of these representative hats. We call them uncoding triples. And theorem says that 2 pointed dyadic triangles with the same orientation of vertices are isomorphic if and only if they have the same uncoding triples. So the last questions concerning The last question concerns isomorphism of representative hats, which is independent from the choice of the pointed vertex. So here we have the following necessary condition. If two representative hats T, I, J, M and T prime, T, I prime, G prime, M prime are isomorphic, then the following two conditions hold. The hats T and T prime have equal or oppositely oriented boundary types, and the areas of the convex hulls of T and T prime in real space are equal. Moreover, if a mapping I is an isomorphism, then it maps the vertex set of T onto the vertex sets of T prime. However, no combinations of these conditions is sufficient. So we need something more. The sufficient conditions we have are formulated in the theorem, which is very long. So I will not give you all very precise conditions, but will rather say general how we solve this problem. Instead of representative hats, we rather used here an equivalent description of so-called almost representative hats, where J and M are positive odd integers as before, but I may be an arbitrary integer. So if we have two almost representative hats, T and T prime, first is a hat of type T, I, J, M with vertices A, B, C, and the second a hat T, K, K, L, N with vertices A prime, B prime, C prime. And let I be a mapping from T to T prime, taking the triple ABC of vertices to the triple XYZ, where XYZ is a permutation of the vertices of the triangle T prime. Then assume that both heads have equal or oppositely oriented boundary types and equal areas of the convex real hulls. Then I is isomorphism precisely when one of 6 conditions concerning these parameters I, J, M, K, L, N holds, and these conditions correspond to the 6 permutations X, Y, Z of the vertices of the triangle T prime. So this is everything. Thank you very much. And here we have some references. This is, of course, not full list of references, but at the beginning we have the paper of Sedley and myself, where is this discussion about how we can generalize convex sets. Then the booklet of Jerzek Kepka, which contain also information about idempotent medial groupoids. Then the next paper is about generation of dyadic convex sets by Matczak, Mućka, and myself. And next one about quasi-varieties of cancellative commutative modes. Then already a little classical paper about dyadic polygons, first one of the series. Then there are 2 new papers written by Anna Mućka and myself when we started to investigate geometry of dyadic polygons, and there is some later papers are in preparations. And finally, this is this basic paper by Walter Neumann on quasi-variety of convex subsets of affine spaces, and our book, Modal Theory, and the second book about mods. So thank you again.
Thank you.